everyone. My name is Miloš Mirković. I'm the project manager and welcome for the Data Science Conference DACH. And welcome to the first tutorial of our conference. With us today, we have Tunjic. He'll be talking about graph neural networks in drug discovery. So Tin, I just want to mention, thank you for coming and thank you for holding this tutorial and opening the tutorials today for us. I won't actually be your host for today. We will have Milica, but I want to join the first tutorial and kind of talk to you and introduce myself and etc. So Tin, whenever you feel like it, you may begin.
Thank you very much on the introduction. I will now just share the screen so that you can see, and then we can start with the presentation. Okay. So my name is Tin Tunjic, and currently I'm working as a machine learning researcher at Celeris Therapeutics. Celeris Therapeutics is a drug discovery company where we design novel drugs in order to target pathogenic proteins. Today, I'll be talking about graph neural networks, first in theory, and second, I will talk about the implementing of the graph neural networks and also how it's implemented in various drug discovery cases and how it's possibly used. First, I will dive deep into the introduction of the graph neural networks and provide us a small motivation of why we even use it. Secondly, I will try to present why molecules are represented as graphs and why is it nice to have some properties that graphs have. Third, I will talk about various graph neural network tasks that can be done, meaning the prediction types and so on. Fourth, the graph data processing, how the information is propagated, message processing, and so on. And the fifth, I'm going to talk only about the graph convolutional network, but of course there are many more and so on. But I will mention graph convolutional network and maybe some other, but we'll stick on graph convolutional network because in the implementation part, we're going to implement our own graph convolutional network and try to predict the toxicity of the molecules that we have in this TOX21 dataset. At the end, I will provide you with a summary of experiments that we did. For example, differences between multitask prediction with a full network and graph convolutional network, differences in the prediction, meaning the metric that we use, and why is it better to use some, for example, poolings and so on in specific tasks. So why do we even want to use graphs? If you look at these three specific examples, you'll see that those data actually look like graphs. Those are graphs. So why not use their how they look like and propagate the information generally how they really are in the reality. Left we have a molecule, which is of course a graph, kind of graph where each atom is a node and each bond is an edge. Then we have a U-bahn of Wien, which is also a graph where each station represents a node and edge is just the connection between those two stations. And third, we have this social network that, for example, tries to look at the various connections between people, and then, for example, if two people are connected, that, for example, they maybe have same interests, they will have the edge together. Now, why exactly is nice to represent molecules as graphs and then maybe also learn on those graphs is because, as you can see, it's a natural way of representing the molecules. You can see here on the right that this molecule, each atom is, as I said, a node, and then for the bonds we have edges. So maybe you can see the double bonds. That's one edge, then a single bond, that's another edge, and so on. So basically, we represent those molecules with respect to their atoms and bonds as nodes and edges. Then they can also include some kind of features. both the nodes and the edges. Nodes can be, for example, atom type, mass, and bonds could be bond type, or for example, if you want to have a 3D graph, which is also a possibility, then you would have a distances or displacements of various kinds. Now, what are the most three common tasks when it comes to graph neural networks? Three most common, but not all. There are many more that you can do with graph neural networks are graph classification, where you have, for example, which you will later see, is a molecule, and then you try to see to classify that molecule. Is it, for example, potent or not? Is it that compound active or inactive? Then second thing is link prediction. You can see that, for example, in this social network, where in reality you would have two people, and then you would like to see if those two people are connected. Because let's say that you want to recommend something to another guy or woman, then what you would like to see is if you already have someone that's similar to them, so that you can maybe get them the same content that the previous person liked. So that's a link prediction. And then also there's a node classification, where for each node of a graph, we try to classify what it is. For example, we could classify it, what type of atom it is, or various kinds of classifications. This is an example of graph neural networks for molecular classification. It is very often used in drug discovery, where you have one molecule and then you try to predict various properties. That is very helpful, because normally synthesizing that drug and having to run this long assays, it's very inefficient, meaning it costs time and money. So if we can have some graph neural network that will predict for us some of the things and maybe minimize the possible space of drugs that could be hit for the target, then that would be a really nice property to have. And this is an example where you have a molecule, you have a graph neural networks, and with this graph neural networks, we try to predict if the drug is potent or not. So basic binary classification. How you do that? Of course, you have to process the information between the nodes. And that's not, I would say, maybe for some of you that are not that in the graph neural network space, it's not as straightforward, because it's not like a convolution where each grid that is near that other grid will be a neighbor. Here, they have to have the same edge. And then with regards to that same edge, the information will be propagated. But what we can see graphs as is a generalization of the images, strict generalization of the images, where each node is a pixel, and the neighboring pixels represent adjacency matrix, meaning the neighboring nodes that are connected with edges to the node. In convolutional neural network, we have a convolutional operator that extracts these image features. What you probably know is, let's say that you have an image which has pixels on each so for the grid space, and then you have, for example, a kernel, and you just slide the kernel and obtain some representation of that image. One of the properties that we need to have for graphs is that graphs are going to be different. They are going to have different number of nodes, different number of edges, and various things. So we have to generalize to operate on arbitrary graphs of the arbitrary length or arbitrary number of edges and so on. On the bottom, you can see one node. This is xi, and its neighboring nodes, which are gray. And you can see this straight lines, right? Those are the information that are coming from its neighboring nodes. And then when we provide with this graph neural networks, then we obtain a latent representation of that node, which is this hi instead of xi. Now I'm going to give you an example how to basically do that and what we need to have to obtain that latent representation. And I'm going to first start with the easiest problem, and that's unweighted and undirected graph. There we have the adjacency matrix, which is nothing other than 1 when I and j are neighbors and 0 otherwise. So basically those are the, if two nodes are connected, they have the same edge, then you know that there's an 1, and if they don't, there's a 0. So we obtain this matrix, and we call it the adjacency matrix. And you, with this information, have the information about which nodes are neighbors to which nodes. We aggregate the neighborhood, so the propagation of the information, by applying this, multiplying this adjacency matrix times this h, which is in first layer xi, so x latent representation, and this weight matrix. And then we also have this non-linearity layer, which is this active, let's say, activation function, so that we have also non-linearity in the latent representation. Now, one of the most known graph neural networks is from Thomas Kipf and Max Welling, which was made in 2017. It's called graph convolutional network. And what they do is, in propagation of the information, what often can happen, if I go back to the last slide, you'll see that this adjacency matrix times this latent representation times weights. If you have multiple message steps, it's going to the features could explode, meaning it will sum up all of the neighboring nodes to latent representations and so on and so on. And if we don't have some kind of, that's called pooling, then features are going to get too big, and it's going to affect our performance when it comes to prediction and training. So what generally graph convolutional network, how they deal with that, they have this degree matrix, which is basically just how many neighbors does one specific node have, and we then make an inverse of that, and also we make a square root of that, so that we can have a symmetric image of the whole propagation of the information. And you can see this is you can also see a node-wise rewritten rule, which is basically just this: n is a neighboring nodes of I, n is the neighboring nodes of j and j, and we just sum up those things and obtain, of course, with the activation functions, the next latent representation. Now, when it comes to implementation part, we're going to be dealing with the TOX21 dataset. That's a pretty well-known dataset, which which is collection of chemical compounds and their toxicological effects, by providing the data on all of the assays that have been run for the target proteins, to see if those target proteins are, if those drug molecules are toxic or not. And it includes binary labels for all of those 12 assays, 12 tasks, where it says, okay, was that toxic or was it not? And if it's toxic, it's active, and if it's not toxic, it's inactive. What can happen is also that when you have these 12 tasks, meaning 12 assays that are run for the 12 different targets, it can happen that 2 or more assays are 1, meaning for the 2 or more targets, the drug molecule was toxic. In the whole data set, we have a little more than 7,800 rows, which are then divided into train, validation, and the test set. Now, today, the experiments that we're going to do are, first, differences, as I said at the beginning, how different the prediction is when it comes to multitask classification network and the graph convolutional network. Those are all out of the box from one library that's called DeepCam. Then afterwards, we're going to write our own graph convolutional network. And afterwards, we're going to see how different pooling techniques, meaning the mean, max, and sum pooling, actually affects the prediction of the model. But before going there, I would like to ask if there are some questions regarding the theoretical part, since when we go into the implementation part, I will mostly focus on the implementation code and various properties and the features. So if everything is clear, we can go into implementation part, but if not, please don't hesitate to ask any questions. Okay. If there are no questions, I will just begin with the implementation part. So, as I said, the graph neural networks are used in many classification tests, especially for the molecules. And one of them that we're going to do today is this toxicity prediction. Now, first, what we're going to do is we're going to install this DeepChem library that we're going to use to train our graph convolution network. So let's do that. And this DeepChem comes also with some nice libraries that we generally I almost use it daily, which is called RDKit. Also one of the most known libraries for the chemistry and so on. DeepChem is basically it's built on top of neural networks like libraries like TensorFlow and PyTorch, and it's an additional abstraction level on top of those libraries. But one of the nice things that they have is that they already come with loader for that specific dataset, so the toxicity 21 dataset, and they also come with graph convolution network completely out of the box and various things that you can just write in 1 or 2 lines of codes, and more or less you have your prediction. We're going to load some libraries, and now we're going to get the dataset just so you can get a sense of how the dataset looks like. Now, this toxicity 21 dataset is like that. So we have these first 12 columns are basically these 12 assays that I was saying. Assays are nothing else than some tests that we do in a laboratory where we synthesize the molecules, and then we see if those molecules have the properties that we would like to have, or maybe the properties that we wouldn't like to have, like the toxicity, for example. Mol ID is nothing else but ID of a molecule, and the smiles is a 1D representation of a molecule. So basically, you will see in smiles, you will see the atoms and all of the various things, and then we can use these smiles to get a 2D representation as a graph with the help of RDKit library. But before doing that, I would like to say that for the active and inactive data points, and especially it happens very often in a drug discovery field, is that you won't have the balanced data set. In most cases, you will have, for example, the molecules that are not potent and some very small amount of the potent molecules. And this is the case for these things. So basically, you'll have the inactive, which is in most cases. And sorry, I just realized that I said that inactive was okay molecule. Inactive was a toxic molecule. So active is a good molecule, inactive is a toxic molecule. And what you see here is that in 92.5% of cases, you'll have the toxic molecules. So meaning in most cases, those molecules will be toxic. So that's a problem that you wouldn't like to have, because once even if it degrades a protein, once it's toxic, it will affect the person that's taking it. By using this RDKit, as I said, we can use this smile and we can obtain the 2D representation of that molecule. As you can see, this is a graph of one of the small compounds, small graphs, and it's a very nice library if you want to visualize certain things. especially when it comes to small molecules, because it's very easy to look at them and to obtain maybe some deeper understanding of what happens there and why some molecule isn't as good as it possibly could be. As I already said, we'll be using the DeepCam library, which is an open source library, which is based upon TensorFlow and PyTorch, like an abstraction layer, and it comes with already pre-trained models, as I said, which is a quite nice property, and also with a loader for the data, which offers us also the featureizer. Before going into the graph convolutional network, we're going to focus on the multitask classifier using molecular fingerprints. But before doing that, I will first like to explain what exactly the molecular fingerprint is. So if you imagine you have a molecule, let's say this one, you'll see that for that molecule, in most cases, when you have different molecules, let's say that you have 10 molecules, some substructures are coming again, right, repeating itself. So what you have, these molecular fingerprints are basically this substructure, like a one-hot encoding. So meaning, like if you have, in a text, it would be a bag of words where you have, okay, how often does this substructure come? Does it come in this sequence and so on, in this smile? And if so, then you obtain there 1. If not, there's a 0 and so on. And of course, you can then normalize it and so on. Multitask classifier is one of the models that was obtained from the DeepCam library, and it's a full network which is just basically made for the classification for the multitask. So meaning when you have multi-class objective, meaning in this case we have 12 tasks for the toxicity report. We would like to see if for each of those tasks, is it a molecule toxic or not? And we do that with this multitask classifier. Also, one of the nice important things that this DeepCam library comes is this loader, and then you have this. You can see this featureizer. This featureizer is nothing else but it already obtains the embeddings needed for us to feed the multitask classification. In this case, this is ECFP. That's an extended connectivity fingerprint. So this is basically what I was talking about. This is molecular fingerprints that we're going to use. So we featureize those data that we have. That's the data that you've seen in the CSV file, right? And then you obtain the featureized versions. So featureized data, those are the those are saved in this dataset object. And as you can see, we already have, for example, the training dataset, valid dataset, and test dataset, which was already splitted into in this low text tox21. And you can see that for the training dataset, we have 6,264 rows, and each of those rows has 1,024 features, and those 1,024 are basically those molecular fingerprints. So meaning, is that substructure coming in this molecule or not? And if yes, then there's a positive number. If not, there's a 0. And basically at the end, we obtain this, our output, our prediction is going to be 12 possible assays. So meaning, is it toxic for this assay? Is it not? For all of those 6,264 rows. As I said, this extended connectivity fingerprint is nothing else than a molecular fingerprint, and it provides us this fixed length bit vector, like I said, up to 1,024 possible features. What also happens here in the loading of the dataset is the transformation of the data. And what you've seen here in the beginning, you've seen that the proportion of the active and inactive data points is quite large, and that could possibly be a problem. And of course, if you don't do some kind of visualization, if you look at the data, one of the possible things that you can do is have some matrix which could be accuracy, and that matrix would not be representative of the data that you have. So we have to really think about how and which matrix are you using, if not using some kind of manipulation of the data. And that's exactly what these transformers do. These transformers is a balancing transformers, so it balances the number of positive and negative example for each task in the data set by oversampling the minority class. So meaning if we have, for example, this in active compounds, it would oversample this active compounds so that we have more percentage of these active compounds, or in the other case, it would undersample the majority class. So it will minimize the number of inactive samples for that specific data task. So yeah, this is that balancing transformer, and how we specify this model is just by specifying this DeepChem models and then multitask classifier. As I already said, we have 12 tasks, 12 assays. Number of features is 1024, and a layer size is nothing else than one dense layer of 1000 nodes, and we have the batch size of 32. So basically, this layer size is, so the length of this list of that layer size is basically how many layers does this network have. In our case, it's only one layer because it's pretty simple, because we don't care now about the optimal performance. We just care about that we get fast prediction and fast training, I mean, and that we obtain the results on that not optimized multitask classifier. So completely out of the box. Also, basically number of features of 1024, that those are the default number of features, and also the layer size is 1000 is a default parameter. So all of this is out of the box. Only thing that's not out of the box is the specified batch size, which we use to train. But everything else is pretty easy. As you can see, that's one line of code with this DeepChem library, and you can already obtain the results regarding the toxicity of molecules. So we're gonna now run that model, and what we'll obtain is the ROC-AUC score. So basically the score, how good do we predict for all of those 12 tasks, is going to average across all of those 12 tasks. So basically it's going to have this false positive rate on the x-axis and true positive rate on y axis, and we're going to have this curve, and the area under the curve is going to be basically our matrix, which is going to say how good this model performs. As you can see on the training set, ROC-AUC score is of course good, but on the test set is 0.67, so 67%, which is not, I would say, not as good. Large difference between the training set and test set. It could mean that we are overfitting, but I'm not going to go into that. But more or less, this is the number that we have to keep in mind when we're comparing that, for example, with the graph convolution network, because we want to see if the graph convolution network also out of the box predicts toxicity better than this multitask classifier. Now, when I go into this graph convolution network, this is a completely out of the box training set. Now, for this graph convolution network, we're not going to specify anything different than this featurizer that is going to actually get us the node and the edge embeddings. So how it does that? It provides us with the data of the toxicity 21 dataset, and then for all of the atoms, it brings the feature embeddings, the node embeddings, meaning all of the features, for example, atom type, and then for the edge embeddings, you get bond types and various things, and we already get that provided by using this load tox21 function and this featureizer as actually a featureizer to get the needed features for our TOX21 dataset to input it into graph convolution network. Of course, the matrix is the same as before, where you see that it's ROC-out score, and this task averager is also the same. It's default. It's averages across 12 tasks, and the mode is classification, this multitask classification. Also, the batch size is 32. We have 12 possible tasks, so multitask 12. And we just fit this model, GraphConv model, which is extension of a TensorFlow graph convolutional model. And we fit this with 10 number of epochs, which is actually the same as in the multitask classifier. And after that, we obtain the ROC-out score, which you'll see that, let's run it so that you can see the scores. And this, in both cases, we use the softmax cross entropy loss for the training of the model. And now in training, you'll see how much better does this actually get with respect to the multitask classifier. Also needed to say is that both models are completely out of the box, meaning no optimization has been done with regards to their parameters. So basically, this is as good difference that you can get as possible, because I'm not trying to optimize for the graph convolution network. I'm just trying to see if already out of the box graph convolution network gives us better prediction, which could imply that the graph convolution network is a much better way of representing the molecule, which intuitively, of course, makes sense, as I already mentioned. Now we are waiting, which is taking a little bit more than the multitask classifier. And once that is done, you'll see the train and validation scores, and we'll see how much better actually that is. After that has been done, we are going to go into the graph convolutional model, which is going to be written for us. So I've written a graph convolution model, and then I've written also the graph pooling so that we can use this different graph pooling techniques to see what is actually the best to use. Now, as you can see, this train scores, it's a little bit worse than what was the multitask classifier, but as I said, it could be that this is already overfitted. But if you look at the validation dataset, you'll see that was 72.4% is now for the graph convolution network, and before it was 67.3. So a little bit more than 5% of improvement, which is quite nice, especially since both the models are not optimized. Now, we're first going now to write our own convolution model, and then I'm going to get into this graph pooling that I also wrote because some of the functions were not possible to abstract out of the DeepCam library. But first, before going into that, I'm first going to present the graph convolutional model for this specific task. As we already did, we specified the batch size equal to 32. Number of tasks is, as we already know, 12. And now we basically just specify the layers. And in each layer, you'll see that we have this batch normalization where we normalize the inputs, which can affect training in many cases. And what most of us know from the practice, with the normalization, we usually obtain almost the same prediction in much faster time in most cases. So basically, by doing that, we increase the speed of training if we want to get to some, I don't know, specific prediction, or I don't know, stopping criterion. And this, as you can see, includes two graph convolutions, two graph convolutional layers. First one has 121 nodes, and the second one also 121, and then we have this dense layer, normal dense layer, where we have 256, and then we just gather the information, and we provide this information into our dense layer again, and we have then softmax function, which actually gives us the probabilities of how probable is that this molecule is toxic or not. For all of those graph convolutions, we use the activation as a 10H, so the hyperbolic tangent function. And this is taken not as something now that needs to be thought of. This is basically, I just took one of the activation functions. Also, this model is not completely optimized model, as you'll see in the prediction. This is just a use case of how you can write your own graph convolution networks, and then maybe optimize your own graph convolution networks, because you may not be happy with the default parameters or whatnot. And also you would like to specify some different things that maybe some library like DeepChem doesn't have, which you'll see that happens for the graph pool layer. Our graph pool is one class that I've written for the graph pooling operation. I already said that once you have the latent representation for each of the message passing steps, so every time the information has been propagated from one node to the other node, you have to have some kind of pooling function, pooling operation, because if not, the features are going to explode. You're going to summarize a lot of features, and especially if one node has very large number of nodes, very large number of neighbors, then it's going to get a lot of information, and that could affect our training tremendously. So by having this graph pooling layer, we actually take this information from all of the nodes, and we propagate it with some function like mean or max, or the sum of those nodes, so the neighbors, and basically obtain our new latent representation for that specific node. This graph pooling needs to normally be in graph neural networks permutation invariant, and what that means is that that's a property where you have one node has multiple neighbors, and if you change the order of neighbors, meaning, for example, this function, this graph pool changes the order of neighbors, how it propagates the information, it should obtain the same results. So if you permutate the neighbors, you will have the same results, and that's exactly what some max or mean operations are, where basically if you change the order of nodes, you'll obtain the same information. For the graph convolution second layer, we have the same thing, activation, as I already said, that 10H, also 121, batch normalization of our batch 32 batch of inputs, and also this graph pooling with the reducer that we can specify as, in this case, mean, max, and sum. And then this layer dense is just a normal layer dense layer, which has 256 nodes, and also it uses the activation as 10H, so the hyperbolic tangent function also includes the batch normalization, and gathers the data, because we need those data gathered so that we can predict for all of those data from that specific molecule, specific property, in this case toxicity. This doesn't have to be the case when you have one node classification. Then for each node you will have one row, meaning like one representation, and then for that specific row you would actually predict some property that you would like to predict actually. And by doing so, then you will have as many predictions as you will have nodes in a graph. But in this case, since we have only one property for one graph, then we have to gather the information all together. So all of the information from the nodes, gather them together, and then actually have the probability of how probable for that molecule, that task, that assay of the toxicity is. And this call is nothing else but the forward function, where basically just forward the information. And as you can see, this GC1 is nothing else than a graph convolution. Then we go into this batch normalization. This output, we have this this graph pooling, and our reducer is actually specified here. So by specifying this, that also comes into play into this output. And the same is true for the second layer. And then for the third layer, we obtain this dense layer. Batch normalization, of course, read the outputs, obtain the logits, and basically apply the softmax to logits so that we can have the representation between 0 and 1, because logits are just unnormalized outputs, prediction outputs. As I said, as our prediction function, we use this softmax function on our unnormalized prediction outputs, logits. Okay. This model will take some more time, so while doing that, I'm going to also specify some other things. This data generator is nothing else but like a generation of the data, obtaining the batches of the specific data so that we can run our specific model on the data that we have for the number of samples in a batch that we have. And we run that data generator on the train data set with number of epochs being 10 as before. And then we obtain how good actually our scores are with respect to the ROC-AUC matrix as before. One of the things that also happens here is that we need to also specify that this convol agglomerate moles is that for each batch, the molecular structures are converted into this convol mole object, which is basically just a data structure to use in this graph convolution network models to actually represent the graph of molecule. One of the things to say is that this, as you can see, is taking a little bit longer, and it's not completely optimized. But I think the most important part here is to get intuition of how to write your own models once having already obtained maybe some out-of-the-box models, because this could provide you maybe some better understanding of the topic and so on. One of the things that I didn't do is this: I didn't specify this graph convolution that's taken from the TensorFlow, but I think I specified it in the theory part, which you have in the presentation. So by doing that there, I don't think it's needed to specify it into the model that we're currently using. You could already see in the beginning that this DeepCam is backend from the TensorFlow and from the PyTorch, which is good for these cases where we can present some of the things, and it's very nice to have all of those things out of the box, easy to predict, and all of the things. But once debugging or some various things, you could have problems with dealing with this kind of library, because then you would need to go into the TensorFlow or PyTorch if it's PyTorch backend, and then you would have to debug the code there, which in some cases could be slightly problematic. Also, one of the things is that I didn't mention, I only mentioned that it's backed by PyTorch or TensorFlow. It's actually backed by both so in some cases it's backed by PyTorch, in some cases it's backed by TensorFlow, and that's one of the properties that Diffkin has, which is just an abstraction layer on top of those. And for the TensorFlow, it's abstraction layer on top of abstraction layer, because Keras is already an abstraction layer on top of TensorFlow. So by doing that, as I said, we have the minimal number of things that we have to do to get the things running. But if you want to have something in production, this isn't the path that normally one would take. So normally one would take libraries like TensorFlow or PyTorch and then develop the code there, since it's much more stable and much more easy to debug. The model training has been finished, and as you can see, the model for the data set, this is 0.89, and then the training set score, so for the ROC score is the 82% for the training set, and then for the test set we have 68%, which is a little bit better than for the multitask classifier. This isn't completely already mentioned 10 times, but still needs to be said. It's not optimized in any case scenario. So also the activation functions are not optimized. The number of layers are not optimized. The number of nodes in the layers are not optimized. So just obtaining this result, which is currently better than the multitask classifier, is nice, and we can see that the model works. Of course, not as good as we would hope, but that also it's dependent on the data set. And since this data set is not just a one task classifier, so meaning the binary classification one task, it's much harder to predict for 12 different tasks. And what you also could see that this data set doesn't have many samples, only 7,800, which we use 6,000 something for the training. So for that small number of samples and models being not as optimized, this result is actually not as bad. And normally in the drug discovery field, in pharmaceutical industry, this model doesn't have to be always 100%, but it has to predict some things better than the other. What I mean by that is, if you have one molecule, it's much more important that we predicted the toxic ones as the toxic than the not toxic ones. Because if we don't predict the toxic ones as toxic, then what could happen is that if you would not run the assays and so on, you would produce a toxic drug, right? But normally, of course, you do all of those things. So basically, this just you would just use this as a filter of all of the molecules that we have. In that case, the best case scenario would be to predict more molecules as not toxic, meaning that we are more comfortable saying and having the true positives in the non-toxic department, because those then will be sent into the synthesis in the lab, and then we will synthesize those drugs and obtain all of those molecules and see if any of them is actually a hit for that specific target. And that's actually what we've been doing it in Celeris. We've been having different filters and obtaining for specific degrader molecules, for specific molecules, if those molecules are hit or not for that specific target. And then by minimizing the space of possible degraders, we were able to synthesize more possible drugs and, let's say, better filter of those drugs than we would normally do. Because normally chemists can only be as good when predicting, okay, is this molecule toxic or not, or is this molecule a hit or not? And it's actually not as easy as one would suspect, because in a lot of cases, the interaction between the protein and the molecule is very hard to see from your own eye. So by having some kind of model in doing so, that's a really nice property to have in your pharmaceutical company, and to have this filtering step where you can use that as a very good space minimization technique to provide chemists with additional information. Graph pooling, now we can go into that, is, as I said, this when we propagate the information, we would like to have some permutation variant function, which could then lead us into mean. In this case, what I implemented is mean, max, and sum. So what I did is I took a graph pool class from the DeepChem library. It's also, as you can see, backed by TensorFlow Keras. And what they previously had, they only had max reducer, so meaning the graph pooling of the nodes where the operator would be the function, maximum function. Meaning if you have, let's say that you have 4 neighboring nodes, you would see, okay, for those 4 neighboring nodes, this specific thing is the maximum, this information is the maximum, this input, and I will propagate only this information into my node and obtain this latent representation. In sum, you sum all of them, and in the mean, you sum all of them and then divide by the number of the neighboring nodes. So this is basically divide by the degree matrix. Like I said before, for example, for the convolution, now there we have the symmetric degree matrix, meaning we take the square root of first degree matrix and the second degree matrix, but this is just taking one square root of, sorry, not square root, this is just taking one degree matrix of that node and basically just dividing the inputs with this degree matrix. This reducer, I implemented this reducer as one additional parameter of the our graph pool class. And what happens here is, at the end, you'll see that if we specified that the graph pooling layer is a max, then we provide this max. If we specify it as a mean, then we reduce all of the nodes to a mean, and if we specify it as a sum, we reduce all of the neighboring nodes into sum. At the end, we obtain those representations, those graph poolings, and have obtained the latent representation later in our graph convolutional network. Also, if there's it can happen that minimal degree is so 0. That happens when one node is 0. One node has 0 neighboring nodes, and in that case, it's impossible to propagate the information if you don't connect, for example, that node with some specific edges. We don't do that here, but in many use cases in the papers and the publications, what they do is they have some nodes. They see that those nodes are not connected with edges, and they specify some radius. Okay, when you have that radius, you can obtain all of the neighbors with that specific radius, and then you just drew the edges and obtain the information, propagate the information with respect to those edges. Also, what you can do when you're doing those things, you're going to have this edge embeddings where you will specify, okay, is this a really bond edge, or is this some edge that was specified because of this neighboring radius? So let's run our graph pooling. We already ran for this max, right? Reducer max, and now what we're going to do, we're going to run for the mean and sum. From the mean pooling and sum pooling. I think this will take some time, but either way, we'll see what makes the most sense in this use case scenario. One of the intuitions behind the mean and so on is that you would like to get the information from all of the nodes, but you would also like to have it normalized in some way so that you can you don't have you don't have the bias if one node has too many possible neighboring nodes. So that's for the mean, and sum is basically just summing operation of summing the neighboring nodes into this node that you're trying to propagate your information to. This takes some time, but the parameters are staying the same. So we also train for the 10 epochs, which all of the models are trained for, and maybe that's underfit, maybe that's in this case maybe an overfit, whatnot. But as I said, this is just a parameter that I have taken, not too much to think about it, just to see how it works and if it works and what actually is the best pooling mechanism with respect to that specific task. Okay. While we are waiting for that, I can also say that in many cases, for the molecules, graph convolutional networks are not the only networks that we use or predict the properties with. So many of the other networks that are most common are the graph attention. So it's called the GATT, the graph attention transformer, and the message passing neural network. And basically those networks are also graph attention so the GATT was obtained, I think, 2018 by Petr Ličkovič and the rest. And the message passing neural network was also obtained around that period. I don't know who the authors were, but also very used message, very used graph neural network in many possible tasks. Currently, there are many new networks every day. Some new graph neural network is coming with different propagation rules, with different properties. But those three are, I would say, the most common and are still very used in very many case scenarios, because graph convolutional network just makes sense from the intuition perspective. Because we actually, as I already said in the beginning, we get from the convolutional neural network, we get to the graph, which is just a generalization of the convolutional neural network. So it's actually a nice property to have that graph convolution as one of the building blocks when dealing with graphs. As we can see, for the mean pooling, we obtained a slightly better result. So you can see the test set score is 68.3. So for 0.3%, the mean ROC-AUG score is better, but I mean that's nothing worth mentioning, right? But still, it's nice to have. It's nice to see that the different pooling provides us with different predictions. And in many cases, what can happen is that pooling techniques could affect the prediction a lot. And we're going to wait a little bit for the sum pooling. The model fit has finished. The model fit is 88%, but that's not the thing that we are going to now to look at. It's not that important. We are more interested into this test set score. As you can see, the sum is the worst of those three, and actually it's worse than 2% than the mean and the max, which says a lot, right? Because it provides us the information that in this case, maybe the graph pooling sum operation should not be used just by the basis of seeing the ROC-AUG score of the dataset. One additional thing that I would like to talk about, and this isn't covered in this implementation part, but it's actually pretty important, and that's graph symmetries. If you gone through the last number of publications in the papers, you've seen that in a lot of cases, some graphs have different properties that you would like to have. One of them were equivariance or invariance. So what those things are actually. And you can imagine that, let's say that you have this graph convolution network, and you have a molecule which is here, right? And let's say you propagate it through the space and so on. You translate it, you rotate it, you reflect it, and so on. And for all of those things, so for the translation and for the rotation, you would like, if you rotated it, you would like to obtain the same basically prediction. So basically, you would like to have the same probability output for this multitask classifier. The same would be true for the translation, so for both rotation and translation, but maybe it would be different for the reflection, because you could have a chiral center, meaning the stereochemistry of a molecule, and then you would like to obtain for that specific molecule, if it's reflected, like mirrored, you would like to have a different output by some amount, for example, negative sign, where normally if you had the invariance, meaning you'll have basically the same output. So what I'm saying is that if you translate, if this algorithm is translational invariant with respect to that output, that when you translate the molecule, the output of the algorithm will be basically the same, because it's invariant. The operations are invariant. You can do as many translations as you want. The output will stay the same. The same is true with rotation. So you rotate the molecule as many times as you want, but if algorithm is the rotationally invariant, the output of the algorithm stays the same. And now for the equivariance, that's actually a property where you would like to have, if it moves by, if it, let's say, mirrors by something, then you would like to have that output is also learned that way, that, for example, if it's positive sign and then you mirror that molecule, so you change the stereochemistry of one molecule or substructure of that molecule, what could happen is that substructure could cause the molecule to be toxic. So you would like to have that output, for example, to have a negative sign in front of the prediction. So that would be a case of equivariant model in the nature. And those are basically used in many cases, and they obtain some very nice properties, especially for the various pharma use cases. One of them could be molecular dynamic simulation and so on. I won't go into that, but as you can see, those things are very important if you want to have your graph neural network to have, let's say, some inductive bias or some various things that you would like your inductive your graph neural to have some basic properties, right? So basically, what we've done here is we've seen that for this data set of toxic assays, 12 toxicity assays for the 12 different targets, we have this different one. Is it active or is it inactive? Or if it's not a number, then that means that assay wasn't done on that specific molecule. And we learned basically with that data set in many algorithms to obtain this multitask classification objective. In all of the algorithms specified before, when using the featureizer, this none is actually transformed into 0. So basically, by having none is saying, which also could be not optimal, right? Because just by not running that, you don't know if that's a toxic or not. So by saying, okay, it's not, so it's inactive, it's maybe getting rid of some information that could be helpful normally. But that's what we do in this use case, because as I said, this is not Jupyter notebooks to get the best result possible. This is just to get an intuition of how we use these various algorithms in the drug discovery field, in the pharma field, to obtain different properties in order to minimize the time needed and the money needed to actually drive those drugs into market, which is of course a tedious project by itself. But by doing some of the things that I already mentioned today, we can minimize the time needed for all of those things. So already said, imbalanced data set, we have the molecules as miles, represented as miles. I'll also give you an example because this is quite small. This data set also has some bigger molecules, so maybe we'll see some of them. An example, let's say for the second one, and we're going to now use also the RD kit that we already used and visualize then this molecule. Let's just smile and also here smile so that we don't repeat the same name of that molecule. And then we have this molecule. Let's see if, yeah, it's a little bit bigger. So as you can see, some molecules are bigger, some molecules are smaller. We provide you with this 2D graph from the smiles, which does this more from smiles function of the RDKit library. And then you can obtain also, if you're interested, all of those pictures of the various molecules. Because in a lot of cases also the chemist can see if the molecule is toxic or not just by looking at the molecule. Not all of the cases, but in some cases, yes. And in some cases, it's very valuable information for the chemist to give him also this visualization or this information so that he can be possible to get the best information possible to get to have the right judgment when it comes to toxicity of the molecule. Then we did this multitask classifier, which was basically just a out-of-the-box full network model. And we obtain the scores of that data set, and we've seen that it's 0.67, so 67% on the AUX score, which is, as I said, slightly better on the graph convolution network for the out-of-the-box graph convolution network, and also for some of the our own written graph convolution network, which is quite nice. So it's quite nice that we know that also by writing our own graph convolution network model and not by thinking a lot about it, we can still obtain better prediction than this multitask classifier. Then we did this graph convolution, as already said. We specified all the needed information. So the classification batch size is 32. We have 12 tasks, and we generated those models, and we obtained those scores. As you can see, 72.4, much better than 67. And for the graph pool, we obtained max, mean, and sum operations functions, which we use then to see which one is actually the best one in this case. We also written our own graph convolution network, where we specified 2 convolutional layers. Then we specified this dense layer, and we gather the information so that we can predict for the whole graph that specific property. Sorry. We feed that into the softmax function to have the output probabilities between 0 and 1, and then we train the model. We had the data generator, which was just used for the batch generation and for the data iteration, and we obtain these scores. And as you can see, as I already mentioned, this test set score 68% is not the best. It's worse than the graph convolution network out of the box, but it's still better than the multitask classifier, which is good since we didn't optimize also this model that we've written. And then for all of the pooling things, we have the mean, sum, and already presented max. You can see that for the sum, the test set score was the worst. So the mean ROC score was just a little less than 66%. and for the mean graph pooling, we had the ROC-AUG score of 68.3, which is slightly better than the max graph pooling. That's basically it. When it comes to implementation and the theory, I would be happy to answer any questions if there are some. If not, that would be basically sorry, something. That would be basically it for today. But please, if you do have any questions, don't hesitate to ask while we're waiting for the presentation to refresh. Okay. So, are there any questions? Anything that wasn't clear? Maybe some of the things that I've said about the graph neural networks are maybe not as easy to understand if you're never interfered with graph neural networks. So I'll be happy to explain whatever question you have in mind, since this isn't an easy topic, especially if you never used some model as a graph convolution network model. So please, I'll be happy to answer whatever comes. Okay, I've just seen the question, sorry. Yes, okay. So this toxicity, I'll now answer the questions. How do I define if the component is toxic? I don't define this. So basically, I have no idea about this information. What this information is coming from, this is coming from a data set, which is this TOX21 data set. That was a competition made in 2014, where all of those molecules that you've seen from the data set were actually concatenated together into this data set, and they then said, okay, is this active or inactive regards to this assay? So with information about the assay, is it toxic or not, you have to take a look at the toxicity data set to obtain more information on that part. Okay, then there was a question about the meaning of the matrix age. Matrix age is nothing less than a latent representation of the node. So basically, in the first layer, you have the X, right, as an input features. That's the representation of the node. But once you start propagating that information, that's called latent space or some kind of embedding space, and age is this latent representation of that specific node. Oh, I'm sorry. I thought that the full screen node was on. This was something that on my screen seemed to was. Okay. In the pharma sector, how necessary is it to have a chemistry or pharmacy background of some sort to be working with data science with them? I would say it like this. It's definitely helpful. It's definitely helpful if you have biology and chemistry, some basic knowledge of biology, chemistry. But I can tell you from my experience that, and now I've been working for the last 2 years in the pharma industry, it's not necessary, right? In many cases, a lot of people that come into the pharma sector, especially that are researchers, machine learning researcher or engineers or data scientists, don't have extensive biology or chemistry knowledge. So what you normally see in the pharma field is that you will have this interdisciplinary teams, where in teams you'll have, let's say, 2-3 chemists, you'll have also 2-3 biologists, and then you'll also have the 2-3 machine learning researchers, whatnot. And that's actually, I think, in my opinion, a very nice way of dealing with this problem, because in most cases, these problems are really interdisciplinary, and it's very hard to have all of the information necessary just by having, let's say, machine learning researchers. Because, I mean, you can only have the prediction as good as your data is. Machine learning is not some magic stick that you're going to point at some data and it's going to predict now perfectly these various properties that you would like to have. So by having this different properties for the nodes, and knowing that those are important generally in the reality. That's nice to know, that because with those information, then you would like to have that information propagated into the graph, and maybe have better prediction than not having them into the graph in the first place. So I would say it's good to have, but it's not necessary. But what I can say is that it's really good to have this graph neural networks knowledge, or the geometric knowledge, which is actually a much bigger field of various possible architectures, not only the graph neural networks. And that's actually what I was saying about this, that's the notions of this equivariance, invariance, and so on. That's what came from this geometric deep learning field, and many other algorithms like gauges or manifolds are introduced there and are quite nice for this non-Euclidean data representation. So the mean, then another question is, why did I choose the ROC-AUG score, mean ROC-AUG score for evaluating model performance? This is actually not, I would say it's not optimal. So meaning what I did by choosing the matrix, the only important thing that I thought about is that I don't use some matrix that's going to be not good for the imbalanced data set, because even though we let's say have more now with this balance transformer, more inactive molecules, we still, I don't think there's a 50-50 percentage of the molecules. So by having some kind of accuracy, something like that, that wouldn't be our optimal metric. So ROC-AUG score is actually a pretty nice metric for the data set which is imbalanced, and that's more or less it. Everybody, the data and the Python notebook and their presentation are available on my GitHub profile. I will actually give you, and actually I think it's given already by the data science conference, but I can also specify it here in some of the answers. Sorry. How do I answer all of them? Is that a possibility? Okay, there's a chat. Now we can see in the chat that you have all of the information needed. So on this GitHub, you'll find the notebook with all of the things that I did, and you'll also find the presentation that I included. Now let's get back to the rest of the questions. Yes, so the code is available to you, and also one last thing to go on the matrix. So this is said, okay, maybe aiming to optimize by recall seems more suitable for the goal to identify real non-toxic or even F1, F2 scores, and so on scores. Okay, so F1 score I wouldn't use, because if you use F1 score and if you have an imbalanced data set, when you rewrite the F1 score, you'll see that in the nominator you have 2 times true positives. So if you have many true positives, then for an imbalanced data set, that's not going to be a very good score, right? So I wouldn't use that matrix, but all of the other matrix and the rest of the matrix are basically okay. Also, one question that I missed from the Olena is, have you considered to use afterwards a classifier calibration to return back to original population, creating by a calibration framework, creating model and some relationship model? That makes 100% sense. I can see your point, meaning now we have different balances, right? But in the reality, we're going to again have more data samples that are toxic, right, than non-toxic. So by having this real distribution of the data set, it's really helpful to have that. I haven't done that, but this is a Python notebook that you can use, and you can fork it and also pull all of your things that you would like to try, or maybe some different things, or try different things with this notebook that I presented. So basically, this notebook is just the intuition part of getting the graph convolutional network to run and to see how good it actually works. Recording of the session, I think it should be available. It should be available on the YouTube, as I recall, and it's going to be available under the Data Science Conference YouTube page. The GitHub link does not appear in the chat. You probably have to set the. Yeah, you're right. You're right. That's my mistake, everyone. So this is the link. Now you can obtain the link and you can go through the Python notebooks. And unfortunately, this presentation is somewhat okay. Then I can just give you as last thing is I can give you my email. So please, if you have any additional questions, you can also email me on this email, and I'll be very happy to answer any questions possible that could arise from this presentation or from this code, and be also very happy to maybe provide you with some additional information regarding getting in the pharma field and how you could leverage your knowledge of machine learning techniques to get into those kind of positions and fields. So that's it from my side, and I would like to finish on saying that I'm happy that you listened to this. Hopefully you got something out of this. Hopefully this was helpful for you. I know this is some, let's say, easy tutorial for the graph neural networks. So anybody who's more experienced with this, maybe didn't have as many positives as some of you that are not coming from this field, but nonetheless, I think it's nice to have the perspective of graph neural networks used in the pharma field, and why is it actually important to have the graph neural network knowledge in order to get into pharma field. Yes. Okay, hopefully I answered all of your questions, and I would like to thank the Data Science Conference and all of the people that are included into this nice conference, and would like to say thank you for all the attention, and probably see you maybe tomorrow if anybody of you come into this conference, and hopefully this Friday from 7 it's meet and greet, right? So thank you all.